Welcome to today's central exercise session in Mathematics 2. As usual, we'll be happy to take your questions on our chat channel. The chat is available here at chat.tum.de. Please log in there using your TUM online credentials. And then you can use this channel here, MA9714-CE, to ask your questions. As usual, the chat channel will be moderated. Today's moderator is once again Island Carlson. Okay, let's get started. So here's sheet number 9. Basically, one problem for the central exercise session today, C91, where we have an optimization problem that we want to solve. And we are going to do this using the method of Korish, Kuhn, and Tucker. And you might have noticed by the manner the questions are stated, this has actually been an exam question in previous years. So let's have a look at this exercise here. C91. We have an optimization problem in 2 dimensions, so 2 variables, x1 and x2. And it's given in this form here: minimize 4x1 squared plus 2, x2 minus 8 squared, subject to x1 is less or equal to 12 minus 2x2, and 2x1 is less or equal to 12 minus x2. And the first thing that we're going to do, if we are given an optimization problem like this, is we always bring it into the form required by Korish-Kuhn-Tucker's theorem. And that is, you want a minimization problem, which we have already, so that's fine. And we have an objective that we'll usually call f. So that's the first part of A. We reformulate that and give names to the proper functions. So here we have a minimization problem over f of x1 and x2. And f is the objective stated above, 4x1 squared plus 2, x2 minus 8 squared. And then we need to reformulate the constraints so that they have the form less or equal to 0. We have 2 constraints here. So formally, we need to define a function, g, that also depends on those 2 input variables, x1 and x2. And that function encompasses the constraints in its components. So we will have a function with 2 components, 1 per constraint. And we reformulate that in a way such that the constraints are written as less or equal to 0 constraints. So that means this first constraint here, we leave the x1 as it is. We take everything else to the left. So that's plus 2x2 minus 12 is less or equal to 0. And this part here, that's the first component of our function g. So that's x1 plus 2x2 minus 12. And we do the same thing for the second constraint, this one here. Again, we bring everything to the left. So we have 2x1 plus x2 minus 12 is less or equal to 0. That's the desired form here, less or equal to 0. So this part here, the left-hand side, this is the corresponding component of our function g. So that's the second component here, 2x1 plus x2 minus 12. So we can write the optimization problem in the desired form. Minimize a function f subject to a function g, a vector valued function g typically, is less or equal to the 0 vector. Okay, so that's the reformulation that the problem statement asks for in part A. Questions so far?
Nothing that I can see so far.
Okay,
Very
wonderful.
quiet.
And let's go right on and see what questions there are after I'm done with the next part. So what we want to do is we want to solve this optimization problem using Kawrish-Kuhn-Tucker. So what we need to do is we need to write down the Kawrish-Kuhn-Tucker constraints. We need to find Kkt points for that problem. And then see if one of those Kkt points is a minimum. And the first thing that you should do in such a setting is have a quick look at the functions and see if you can establish that the objective and the constraints are convex functions. And that is indeed the case here. So as you can see, those G components here, those two functions, those are affine functions. Right? Linear functions plus some constant. And affine or linear functions are always convex as well. That's a special case of convex functions. So that means our components of G are convex functions. And the same is true for the objective. That's also a convex function. Now you might not see that immediately, but we can easily infer that from looking at the Hessian of that function. We need the gradient anyway, so let's do that right away. So let's put this as part of A still. So what we do is here we compute the gradient first. Now taking the derivative of this function here with respect to x1, that yields 8x1. And with respect to x2, we get, let's see, x2 appears here. So we get 2 times 2 times this expression here. So 4x2 minus 8. Right? So this here is the gradient, or in other words, 8x1 and 4x2 minus 32. Okay. And once we have that, we can easily come up with the Hessian as well. So the Hessian here is, we take the gradient, we first differentiate the first row of the gradient with respect to x1 and then x2. The partial derivative with respect to x1 is just 8, and there's no x2 in there, so the partial derivative with respect to x2 would be 0. And then for the second row, we do the same thing. Differentiating that with respect to x1 yields 0, and differentiating with respect to x2 yields 4. So we can see that with 8 being strictly positive, so this 8 here, and this determinant well, that is 8 times 4. That's also strictly positive. That means HF is positive definite. And that means we do have a convex function. So that function is convex everywhere because the Hessian does not depend on the x variables. Okay, so F is a convex function. Okay, so we have established that both G and F are convex functions. And basically that means that every Kkt point we will find will also be an optimum. The one thing we have to look out for is we need to make sure that the constraint qualification holds, the Slater condition in this case holds. That means there is a point that satisfies the constraints strictly. And if we look at these constraints here, we can easily see that, for example, if we take x1 and x2 to be 0, then the only remaining part is -12 and -12. And this is, of course, feasible because that's less or equal to 0. And it's even strictly less than 0. So as g of 0, 0 is -12, -12, which is strictly less than 0 and 0. That means this later condition is also satisfied. So the extended version of Kkt's theorem can be applied, right? That means a Kkt point will not only be a candidate for an optimal solution, but it will always be an optimal solution. Being a Kkt point is already sufficient for being optimal. So basically, that's pretty much a comment on what we need later in that problem. We wouldn't have needed to do that at this point, but I'll come back to that later anyway, so why not do it right away? Okay, let's write down the Kkt conditions finally, part B. So we want to have Kkt points, and the Kkt conditions basically consist of a Lagrange-like condition, feasibility, and complementarity constraints. In this case, we have two components in that function g, two constraints, two inequality constraints, and we need one multiplier for each of those inequality constraints. So we'll have two multipliers here. Let's copy that problem so we can have a look at that while we come up with the Kkt constraints. Yeah. Down there, maybe a little smaller, that should do it. Okay. All right, so let's start with the Lagrange condition. That basically is the gradient of f at the point x1, x2, plus the Jacobian of g of the constraint function transposed times the multipliers. And as I said, we'll have two multipliers here, one per constraint. So let's say the one associated to the first constraint will be called y1, and the one associated to the second constraint, we call that y2. So we multiply the transposed Jacobian with that vector of multipliers, and that needs to be the 0 vector. Okay, so that's the first condition. Then we need feasibility, which basically means g of x has to be less or equal to 0. Again, 0 vector. The multipliers associated to inequality constraints need to be non-negative. So we want y to be non-negative. And finally, we want the complementarity conditions, which in short can be written like this. We have y transposed times g of x is equal to 0. And basically what that means is you have y1 times the first condition, the one associated to y1, times x1 plus 2x2 minus 12, plus, and then y2 times the second condition, this one here, 2x1 plus x2 minus 12. That needs to be 0. Well, and that means through the constraints here, the y's are both non-negative. The g's are non-positive. So here we have a positive sign or 0. Here we have a negative sign or 0. So each of those two components here, this one and this one, could be 0 or negative, never positive. That means if the sum is going to be 0, then each of those components has to be 0. Yeah, so that here basically is just a pretty short way of saying we want this product here to be 0. And we also want the second expression here to be 0. And being a product, that of course means either that first factor is 0 or the second one, or both. Same here, either that is 0 or the second one, or both. Yeah, so those are the complementarity conditions. Let's apply that to the problem at hand. I want to copy that again here. Okay, so first we'll need the gradient of f. We've computed that one already. Well, remember the gradient of f at x1, x2, that was 8x1 and 4x2 minus 32. And then we want the Jacobian of g, so we need to compute that. Okay, let's see those. This here is g. So let's start with the partial derivatives with respect to the first row. That is 1 if we differentiate with respect to x1, and 2 if we differentiate with respect to x2. And for the second row, we get a 2 if we differentiate with respect to x1, and a 1 if we differentiate with respect to x2. So that's the Jacobian of g, and that's constant everywhere. Okay, so we can now write down this condition here, this first condition. What we get there is we have this gradient of f plus, so this is the gradient of f. Then we get the transposed Jacobian. So transposing this results in the same matrix in this case. It's a symmetric matrix. So this is the transposed Jacobian of g. And we need to multiply that by y1, y2. And that's supposed to be 0 and 0. Okay, so if we compute that multiplication, the product here, what we get in the end is one equation per line. So 2 equations in those 3 variables. And then we have these feasibility constraints here. If we write those down, maybe let's write that down in the form of 2 actual constraints, 2 actual equations here. So that's 8x1 plus y1 plus 2y2 is 0. And the second one is 4x2 minus 32 plus 2y1 plus y2 is 0. Then we have the feasibility constraints. So the g is less or equal to 0. That still needs to hold. So basically, we just need to copy the constraints here. The first one is x1 plus 2x2 minus 12 is less or equal to 0. Let's copy that as well. Yep. And the second one is, 2x1 plus x2 minus 12 is less or equal to 0. Then we have the conditions on the y's. So y1 is greater or equal to 0 and y2 is greater or equal to 0. And finally, we have these complementarity constraints here. We write them in this way here. So we get y1 times x1 plus 2x2 minus 12 is 0, and we get y2 times 2x1 plus x2 minus 12 is 0. So this completes the Kkt conditions. start here and end here. Okay, and as we stated before, any solution to that set of equations and inequalities is a Kkt point, and due to convexity and due to the Slater condition being satisfied, any Kkt point will be an optimal solution of our problem. So this concludes part B. Are there any questions so far?
So there's one, which, I mean, you basically answered it, but maybe we can say it again. So it's important to know if f of x is convex because of the minimizer, but what does g of x being convex tell us? Is the question.
So what g of x being convex tells us is that the feasible set, the points that we're optimizing over, is also going to be a convex set. And that's one of the conditions for this extended version of the Kkt theorem. So without that knowledge, we could only say each Kkt point is a candidate. So the minimum, if it exists, has to be among the Kkt points. Together with this convexity of both objective and constraints, we can even state that any Kkt point will be an optimal solution. Yeah, so it will be sufficient to come up with just one Kkt point. And once we find one Kkt point, we can be sure that's an optimum. Otherwise, we'd have to list all possible Kkt points. We'd have to make sure that a minimum actually exists, and then we'd have to find the one among that list of candidates. We have to find the minimum. And generally, if we don't have convexity, not every Kkt point will be an optimal solution to this problem. Have a look at the last sheet. That has plenty of examples of that kind. Any other questions?
No, that's what I see so far.
Okay, so let's continue with part C then. So this is kind of a shortcut now. The problem does not ask us to actually compute an optimal solution using our Kkt conditions. It asks for looking at the point 4, 4. So we have a point x star. That's 4, 4, that's given. And the question is that point an optimal solution to the optimization problem? And of course, the answer could be no, yeah? You should be aware of that possibility, even if that was an exam question. Now, what we have to do, we already stated that every point that fulfills the Kkt conditions will be an optimal solution. And of course, every optimal solution has to be a Kkt point. So with convexity and with the Slater condition being satisfied, we can state that the optimal points are exactly the Kkt points in this problem here. So due to convexity and Slater condition, the optimal solutions are exactly the Kkt points. So what we have to do is we have to verify whether this x star is a Kkt point, then it will be an optimal solution, or not, and then it will not be an optimal solution. So the question is basically, is x star a Kkt point? What that means is, are there suitable multipliers? Are there y1, y2, such that all these conditions here will be satisfied? So in other words, are there multipliers y1, y2, such that x star, y1, and y2 satisfy the Kkt constraints? And to see that, basically, we just have to take this Kkt system and try to find a solution for the given values of x1 and x2. And that's what we're going to do. Let's first copy all that. So we can possibly have it in one page. So here's KKT part 1. Yeah, damn it. Here's KKT part 2. So those are the conditions that we need to satisfy. And looking at the values for x star, 4 and 4, we can just substitute that into these equations here. So with x star being 0.4 and 4, we just substitute that. And we get an equation or inequality system that doesn't contain x1 and x2 anymore. So here we get 8 times x1, 8 times 4, that is 32. Plus y1 plus 2y2 is 0. Here we have 4 times x2, that's 4 times 4 is 16, minus 32, that's minus 16. Plus 2y1 plus y2 is 0. Then here we get 4 plus 2 times 4, so 4 plus 8 minus 12. 4 plus 8 is 12, minus 12 is 0. So you have 0 less or equal to 0. Same here, 8 plus 4 is 12, minus 12 is 0. So the point x star is feasible, and that's important, right? Even if you could find y1 and y2 that work, you have to check for feasibility. The point x star is not feasible. Obviously, it can't be an optimal solution to the problem. Don't forget about that, please. Then the y's need to be greater or equal to 0. And finally, these conditions here, we already have established that this here is 0 and this here is 0. So the y's can really be anything. They don't have to be 0. And they don't have to be greater than 0, right? They could also be 0, but they don't have to be. So these here are satisfied anyway for every possible choice of y. So that leaves us with these two equations and these two inequalities. And from the two equations here, we should be able to solve for possible values of y. So let's try that. So we want to solve this equation system here. Let's reformulate that a little. It can be written as y1 plus 2y2 equals minus 32. And 2y1 plus y2 equals 16. So we can use simple Gaussian elimination to compute the result here. So that's 1, 2, right-hand side minus 32, 2, 1, and right-hand side 16. So let's just subtract 2 times the first row from the second. And we get, let's see, there's a 0. Then we have 1 minus 4, that's a minus 3. And 16 plus 2 times 32, that's 64. So that's 80. Correct? So that means we get y2 equals minus 80 over 3. And y1 equals minus 32 minus 2 times y2. So that would be minus 32 plus 160 over 3. 32 times 3 is, let's see, 96 or something. So that's minus 96 plus 160. That should be 64, if I'm not mistaken. Over 3. So those are the unique solutions to the system. That means this is the only possible choice of multipliers. And now we have to check whether these two multipliers together with the x values that were given fulfills all the Kkt constraints. Well, obviously those are satisfied here. Those are satisfied, but those here are not. You will have noticed that y2 is a negative number. And that's the problem here. So this here is less than 0. And that means y2 does not satisfy the constraint y2 is greater or equal to 0. But there is no other solution that fulfills the other constraints, the equality constraints. And that means there are no suitable multipliers such that x together with those multipliers is a Kkt point. And that can only mean x star is not a Kkt point. And thus not optimal. And notice that to get to this point, we wouldn't even have required convexity, right? So the simple version of Kkt states that every optimal solution is also a Kkt point. So if a point is not a Kkt point, then it cannot be an optimal solution either, right? So we would only have required convexity if we wanted to state that this was an optimal solution, which we'll try to establish in just a minute. But let's see if there's any more questions about this point here.
So I have a couple of questions.
Mm-hmm.
So we defined regularity by convexity and Slater condition is one.
Yeah, so what did I say? The Slater condition? Somewhere up there, right? Here, Slater condition, yeah?
So the question was if we defined regularity by the Slater condition and convexity. I wondered, or I asked back what he meant by regularity because I'm not sure what's meant in the setting, but
yeah, me neither. I think I didn't use that term actually.
So in the Wiki article, it's used.
Maybe sometimes one uses that term. Yeah, so you could say regularity means convexity of objective and constraint functions, and also some kind of constraint qualification is satisfied. Now, Slater condition is one possible constraint qualification, the only one we discussed, and that's usually one of the easiest to see. There's a couple of others out there, just in case you stumble upon those.
But this is the one they're supposed to know.
This is the one you're supposed to know.
So maybe don't get lost in the other conditions.
Yeah.
And then there's one question. What should we do if the functions would not be convex?
Where the functions would not be convex up to this point, we wouldn't really have required that, right? So, to falsify that point here, to state that this cannot be an optimum, they don't have to be convex. Because in any case, any optimal solution will always be a Kkt point, no matter if the functions are convex or not, no matter whether Slater is satisfied or not. Right? So this direction is always true. The other direction might not be true. So you would require convexity to establish that a point is an optimum. And as I said, we'll discuss that as an addendum in just a minute.
And that's what I have so far, I guess. In a minute is now.
So that does officially conclude the problem statement here. But let's still go on and see if we can find an optimal solution to that problem. Right now, the only thing we know is that the point given to us, that x star point, is not an optimal solution. Of course, the more interesting question is, what is an optimal solution? So let's add a part D here. It's kind of a bonus question. Find an optimal solution. So what do we do to find an optimal solution? Again, let's recall the Kkt conditions. Let's see. No, that's wrong. Where do we have the Kkt conditions here? So here's our Kkt conditions. What you stated already. A little smaller, so I hope you can still read that. So those are the Kkt conditions. And we want to find a solution to all of these Kkt conditions. So we want to determine x1, x2, and y1, y2, such that all these Kkt conditions hold. How can we go about that? Well, usually what you do is you try to make a case distinction to check for cases of the multipliers. And what you include in your case distinction is certain combinations of multipliers being 0 or non-zero. Problem here is you only have these two equations. And of course, we can solve equation systems, but there's 4 variables in there, and we only have 2 equations. So there's not enough equations to solve that system uniquely. All the rest are just inequalities. And we don't really know how to deal with those in general. What we also have are the complementarity constraints here. Those would also be equations, but they're not very nice equations because they're nonlinear, right? On the other hand, if we knew that, for example, y1 was strictly positive, non-zero, then that would mean this here would have to be 0. And that would give us another equation. So what we're trying to do is we're trying to find enough equations through a couple of case distinctions and then solve the equation systems for each case until we can finally come up with a valid Kkt point. And that's where we need convexity, because we know that once we find any Kkt point, it will be an optimal solution. So we don't necessarily have to go through all the cases, collect all the possible candidate points, and then find the one that works best. But we can stop once we have found one Kkt point. Okay, so the idea is to find any Kkt point. So due to our convexity and Slater, that will be an optimal solution. So let's first start with a case that we have already solved, just to get that out of the way. You remember that for x1 and x2 being 4, these two factors here were 0. And you can easily see that these two equations are linearly independent. So 4, 4 is the only solution of this is 0 and this is 0. And that corresponds to the case that both multipliers are non-zero. Right? In that case, these equations need to be fulfilled, which means x1, x2 has to be 4. And this did not lead to a solution, as we already know. So that's our case 1. First case, y1, y2 are both strictly positive. In that case, state it again, those two equations here need to be fulfilled at equality. It's easy to see that those are linearly independent, and we already know a solution. So that's the unique solution, right? Linearly independent equations. Thus, x1, x2 equals 4, 4 is the unique solution However, that leads to a contradiction, as we have seen that implies, I think it was y2 being negative. So C part C of this problem. Right, so and of course that conflicts with our assumption here that y2 was actually positive. So there is no solution with that property, y1 and y2 being positive. All right, so let's try the next case. Next case is exactly one of those two is positive, and the other one is going to be 0. And we'll start with y1 being positive and y2 being equal to 0. And notice that this way, y2 equal to 0, we have one equation, one more equation, right? And the y1 greater than 0, that will give us the next equation. So again, here's the Kkt conditions. So if y1 is positive, that means this equation has to be fulfilled. That has to be 0. Right, so from that we get x1 plus 2x2 minus 12 is 0. And of course, those two equations here also hold, and we already know y2 is 0. So we'll substitute that right away. So we also have 8x1 plus y1 is 0. And we also have 4x2 minus 32 plus 2y1 is 0. Okay, so we've used this equation here already, and we have 3 remaining equations and 3 remaining variables. Those are even linear equations, so it shouldn't be so hard to solve them. Let's collect those equations first and bring them into the proper form. So here we have x1 plus 2x2 equals 12. Then I'm going to take this one here next. That is 4x2 plus 2y1, sorry, 2y1 equals 32. And finally, we have this middle equation here. That's 8x1 plus y1 is 0. And if we solve that, we can use Gaussian elimination for that. So we have 1, 2, 0, right-hand side 12, 0, 4, 2, right-hand side 32, and then we get 8, 0, 1, right-hand side 0. And now if you want to solve this, we subtract 8 times the first row here from the third row. Let's see, we copy the first 2 rows. And we get 0. Then we have 0 minus 16, so that's minus 16, and 1. And 0 minus 8 times 12, 8 times 12 is 96, so that's minus 96. And then we can see we can eliminate that entry here by adding 4 times that second row. And let's see, let's copy the first row again. For the second row, we can already divide by 2 to make that a little easier here. And then let's add that row 4 times to the last one. And we get, of course, a 0 here first. Then we get another 0. Then we get 1 plus 8 plus 4 times 2. So 1 plus 8, that's 9. And 4 times 32 minus 96, that should be 32. All right, and now we just need to solve that system. Remember the last row here that corresponded to y1, not y2. And those here were the x rows, x1, x2. So if we do backward substitution to solve that, we get y1 is 32 over 9. And that is non-negative. That is actually positive. So looking at our case distinction here, y1 needs to be positive, and it actually is. And then let's have a look at the x's. So let's see, we get x2 is 1 over 2, 16 minus y1. That means we get 8 minus 1/2 times y2. So that's minus 16 over 9. 8 is 72 over 9 minus 16 over 9. So that should be 6656 over 9. And finally, x1. x1 is 12 minus 2x2. So 12 times 9 is 108. 108 over 9 minus, and 56 times 2 is 112 over 9. So that would be 4 minus 4 over 9. Okay, so we have x1 and x2. Now let's have a look at the Kkt conditions once again. So we have already used this constraint and this constraint. So those obviously hold because we used them to solve the system. With y2 being 0, this constraint here, of course, holds, and this one holds as well. y1 is strictly positive, so that works. And we also use that last condition here to solve our system, so that holds as well. So finally, last condition left are these two here. So we need to verify that those hold. Again, that condition here is, of course, the same as this one. And we've already established y1 is positive, and we use that the green condition is 0, so that will be satisfied. But we still have to check the last one. So this remaining condition here, that needs to be satisfied by our solution. And please don't forget to check these conditions. It might still happen that that condition might not be satisfied, and then we don't get a Kkt point. So let's see. That's 2x1 plus x2 minus 12. 2x1, that is minus 8 over 9 plus x2. x2 is 56 over 9 minus 12. 12 was 108 over 9. Okay, so obviously that is something negative. Plus 56 minus 108 minus 8, that's obviously negative. So we get something that is less or equal to 0. And that means our last condition is also satisfied. So we can conclude that, in fact, the point x1, x2, y1, y2, this point here, with x1 being minus 4 over 9, x2 being 56 over 9, y1 being 32 over 9, and y2 being 0. That is a Kkt point. And thus, again, due to convexity, and later, as we stated before, the point -4/9 and 56/9 is an optimal solution. So we have actually found the desired optimal solution this way. And of course, we were in luck. Our second case distinction already worked. That need not be the case, of course, depending on which cases you use first. Maybe you'll have to do a lot of work, find a lot of contradictions until you actually hit a Kkt point. There might only be one. There could, of course, be many, but again, you might be in luck or not. So, questions?
Yes, I have a couple. So, can you always prove convexity with positive definiteness?
If a function is convex, then yes, you should be able to prove convexity with positive definiteness.
And then,
yeah.
I mean, so I realized when I answered, or afterwards, another question is, how do we know that g of x is convex as the Jacobian matrix is indefinite?
Let me just add something to the answer of the first question, because I just thought of a counterexample. Sorry about that. Obviously, the all zeros function is convex as well, and it doesn't have a positive definite Hessian. So no, you can't. Sorry, there might still be these very flat cases where it doesn't work.
Yeah, which is also the case for g of x. How do you show that g of x, so your constraint conditions, are convex? They're just linear.
Yeah, so what I argued there is both components. So we're only talking about big components, individual components. Each of those is an affine function, and affine functions are always convex. That was my argument.
Yeah, that should work equally well. Okay, and then I have another one. So other than 0, 0, can we choose any point in order to satisfy this later condition? Is there a reason you chose the origin?
Because it's easy. You just need a point where g of x is strictly less than 0. So all components need to be strictly negative. Yeah, we need something that satisfies all conditions strictly, not with equality. Anything that does this will work. I just choose 0, 0 because it's easy to see.
Okay, and then so there's a follow-up. Before we talked about what you do if the functions are not convex, and then the follow-up is how do you know if the points you get are optimal points?
So basically, if the functions are not convex, you would first have to establish that there are optimal points. The usual argument would be the feasible set is compact, and the objective function is continuous. That's most often the case. If that's not the case, then you might be in trouble, and you may be better off asking a professional. So that way you would establish that there is a minimum within the feasible set, and then you simply compute all the possible Kkt points and find the one with the least objective value. And that must be the minimum, or one possible minimum. There might be maybe several. Yeah, so you can't just use the first Kkt point that you get, as we did here, but you have to compute all of them. There might be non-minima among those Kkt points.
So this is exactly the next question. If you would have only the simple case of Kkt, we would have to compute all candidates, right?
Yes, correct. And you have to go on with your case distinction until you finish with all the cases, possibly gotten a handful of Kkt points, and then you select the one with the best objective value.
Okay, and then, so I think those were the questions I see for now for the exercises, for the exercise today, but there were also a couple of questions about the quizzes. So they wonder how they're doing, and also if you can open them for practice before the exam.
Feedback from Julius, actually. I'll have to remind him again. I'll write him an email right afterwards.
But basically, we have decided we will open them. They just
yes, we will open
actually
them.
Open.
He just needs to do it.
Yeah, guess that's at least helpful to know. And then how they're doing on the quizzes. You also don't know?
Yeah, again, I don't know. I haven't received feedback on my questions yet. I'll have to remind him again.
But as soon as you get it, maybe I'll post it in Moodle. That's what I said the last time as well.
Yeah, that's what I said the last time. I remember now. Yeah.
Uh-oh.
Probably the weather's just too nice to be thinking about quizzes.
And then our poor students have to think about the exam. Okay, so I have another one that showed up. If we assume the simple KKT case and only find one solution, this must be an optimum as well, right?
If you have established that there is an optimum, then yes. Yeah, if you have only one candidate and you can be sure that this function has an optimum, then that, of course, must be the optimum. That's right.
Yeah. Okay, then I don't see anything else. I haven't forgotten anything.
Okay, then I guess
think that's it.
Can conclude the social exercises for today. So thanks a lot to Eileen for moderating. Again, if you have any more questions, as usual, you're welcome to ask in the tutorials about any sheet, about any problem, about anything connected to the lecture. Join us on Thursdays, 2 o'clock to 5 o'clock, live on Zoom. The link is on the Moodle page, as pretty much everything you need to know. So I hope we'll see you then. Goodbye.